Welcome back to the deep dive. This is where we take your source material, dig into it, and pull out the most valuable knowledge and, well, surprising insights. Think of it as a shortcut to being truly well-informed.
And today, we're exploring something absolutely fundamental, the very building blocks of the physical world around us, matter and materials. Our source material for this deep dive comes from excerpts of a Grade 8 learner guide, giving us a clear foundational look at these concepts.
Right, so our mission here is to navigate these core ideas, from the smallest particles to how substances interact and change, and distill the key takeaways and interesting details. We'll connect these foundational concepts to what you likely already know, quickly and clearly, finding the profound within the simple. Let's get started.
Okay, let's unpack this. When we talk about matter, the absolute starting point, according to our source, is the atom.
The source calls atoms the smallest particles that build elements. The ultimate tiny unit, in a sense, yeah.
And the word itself tells a story, doesn't it? Atom comes from the Greek atomos, meaning indivisible or not cuttable.
But here's where it gets really interesting, and the source makes this crucial distinction. While that word meaning holds true for chemical reactions, where atoms are only rearranged, never created, or destroyed atoms can actually be split.
They can.
Into smaller parts.
Yeah.
It takes a lot of energy, though, right? Happens during processes like nuclear fission.
Precisely. So the indivisible idea is more about chemical identity, not its physical structure. And what is their structure? Well, atoms are made of even smaller subatomic particles, protons, neutrons, and electrons.
Right. You've got the central nucleus, which packs in the protons and neutrons, heavy stuff in the middle. And then the electrons are found somewhere around that nucleus, kind of buzzing about.
Exactly. And their charges are absolutely key to how they interact. Protons are positive, neutrons are neutral, no charge, and electrons carry a negative charge. A neutral atom, the source reminds us, balances these out. It has an equal number of protons and electrons, making the overall charge 0. The number of neutrons, though, that can vary for the same element. That gives you isotopes.
So everything we see, touch, and feel is ultimately built from these microscopic structures, mostly empty space, actually, held together by forces and defined by the balance of these tiny charged particles.
It's quite mind-boggling when you really stop and think about it.
All right, so atoms are the building blocks. When you have atoms of the same kind, you get an element. But with over 100 known elements, how on earth do we keep track of them all?
That's the job of the periodic table. Our source describes it pretty simply as a tabular arrangement of chemical elements.
And this genius idea came from the Russian chemist Dmitry Mendeleev back in 1869. I mean, imagine the insight required to figure out this arrangement back then.
What makes it so powerful, and this is the core insight behind its arrangement, is that elements are organized not just by increasing atomic number, which is the number of protons, remember, but also by their recurring chemical properties. This periodicity, this repeating pattern, is why elements in the same column or group tend to behave similarly in chemical reactions. Okay. So the structure of the table actually predicts behavior. That's clever. The horizontal rows are called periods, and the vertical columns are groups or families. And the symbols are standardized, usually one capital letter or a capital followed by lowercase, like H or he.
Exactly. And the table broadly categorizes elements, too. You typically find metals over on the left side, nonmetals on the right, and then you have the semi-metals or metalloids kind of bridging the gap between them.
The source highlights some property differences, too, like metals often have high melting points, and they're good conductors of heat and electricity, generally unlike nonmetals.
And here's a cool, surprising fact the source points out. Mercury and gallium, they're the only metals that are liquid at room temperature.
Really? Just those two?
Yep. Every other metal you usually encounter is solid unless you heat it way, way up.
That's the kind of detail that sticks. The source even listed the first 20 elements and gave some fun mnemonics to help remember them. Something like, hi, he lies because boys cannot operate firearms for the first 10. A handy memory tool, I guess. Definitely useful for learning the list, yeah. Those mnemonics can be helpful.
Okay, so we have atoms, and elements are made of one type of atom, all organized nicely on the periodic table. What happens when different types of atoms bond together?
Right, that moves us into the world of pure substances, specifically compounds. The source defines pure substances as having a uniform chemical composition throughout. They're made of only one type of atom or one type of molecule.
So elements are pure substances because they're just one type of atom. Simple enough.
Right. And compounds are also pure substances, but they are made of atoms of two or more different elements chemically bonded together.
The key insight here, as the source really emphasizes, is that they bond in fixed ratios. Like water is always H2 hydrogens for every one oxygen, every single time. That consistent fixed ratio is what gives compounds their specific predictable properties, which are often totally different from the properties of the elements they're made from. Think about hydrogen and oxygen gas versus liquid water.
It's where complexity really starts to emerge from these simple building blocks. The source also clarifies the term molecule. It's two or more atoms, could be the same or different elements, held together by a chemical bond. Crucially, a molecule is the smallest unit of a compound that still has the properties of that compound.
Got it. So atom is the smallest unit of an element, molecule is the smallest unit of a compound. Makes sense. And to form these compounds, atoms have to undergo chemical reactions to create those chemical bonds.
And if you want to go the other way, if you want to break a compound down, the source notes you can decompose a compound using energy. That could be through another chemical reaction, or using electricity, that's electrolysis, or just heat. The example of electrolysis breaking water back into hydrogen gas, H, and oxygen gas illustrates this perfectly.
Speaking of hydrogen and oxygen, the source mentions some elements form diatomic molecules. What does that mean exactly?
Yes, diatomic. It just means their natural stable form isn't single atoms, but two atoms bonded together. Hydrogen, H, and oxygen are prime examples. The source actually lists 7 such elements, the common ones you read into. And it provides another mnemonic, if you like those. Highly naughty fish often ignore chemical boundaries. HNFOICLBR.
Huh. More mnemonic fun. Okay, so we have pure substances, elements, and compounds, but often things aren't chemically bonded, right? They're just kind of mixed together.
Exactly. That leads us nicely to mixtures. The defining characteristic of a mixture, the key difference, is that the substances in it can be physically separated without breaking any chemical bonds.
And the source lists some pretty simple physical methods you've probably seen or even used. Hand picking, maybe sieving, filtering coffee, using a magnet for iron filings.
Evaporation to get salt from water, distillation, even chromatography for separating inks. Basic physical processes.
Right. And mixtures exist on a spectrum, from uniform to non-uniform. If the composition is the same throughout, so you can't really see the different parts, it's called homogeneous. The source gives examples like air, salt water, which is just water with dissolved substances, and even alloys like steel or bronze.
Yeah, and the source also lists things like concrete and milk as homogeneous. That might surprise some people because, you can sometimes see variations. But it highlights how homogeneous often means uniformly mixed at a certain scale, maybe the microscopic level.
Okay, it's about the scale you're looking at. Makes sense. So on the other hand, if the mixture is not uniform and you can clearly see the different components, it's heterogeneous. Muddy water is the classic example the source uses. You can see the dirt particles, they don't dissolve, they just hang there or settle out.
Exactly, the parts remain distinct.
Okay, let's shift gears slightly. We've talked about what matter is. How about how it behaves? The source introduces something called the particle model of matter to explain states and changes.
Right. But first, maybe just defining matter itself. The source says it's anything that has mass and occupies space. Pretty straightforward. And it explicitly excludes things like love, heat, or light because they don't have mass and volume in that same physical way.
Simple but essential context. Okay, so the particle model. What's the core idea?
The core idea is really simple but powerful. All matter is made of very small particles that are always moving, or vibrating at least, always in motion.
And this model, this idea of moving particles, it explains the familiar states of matter. Gases, liquids, and solids, right?
Precisely. The source highlights the key differences in how the particles behave in each state, and these differences determine the substance's overall macroscopic properties.
So let's walk through that. In gases, the particles are really far apart, right? They're moving randomly and super fast.
Very weak forces between them. They just expand to fill whatever container they're in, no fixed shape or volume.
Okay. Then in liquids, particles are much closer together. They can still move, slide over each other.
Yeah, the forces are stronger than in gases, but not strong enough to lock them in place. So liquids take the shape of their container, but they do have a fixed volume. They don't just expand indefinitely.
Right. And finally, solids. Particles are packed very close, often in a regular pattern, like a crystal.
Held by strong forces. They can't really move around, they just vibrate in their fixed positions. That's why solids have a definite shape and a definite volume.
It's fascinating how these simple differences in particle behavior, how close they are, how fast they move, how strongly they attract each other, explain why, ice is rigid, water flows, and air fills the room.
Yeah, it connects the microscopic world of particles to the macroscopic world we experience.
Exactly. And changing the temperature directly influences this particle motion, which is what causes changes of state.
Standard changes like melting, solid to liquid, freezing, liquid to solid.
And evaporation or boiling, liquid to gas. Knowing melting and freezing points is really practical. The source notes, like for storing food safely, things like that. But the source highlights a fascinating, less common one. Sublimation. What's that again?
Sublimation. This is where a solid changes directly into a gas, completely skipping the liquid phase altogether.
Okay, any examples?
Dry ice is the classic example the source uses. It's solid carbon dioxide. At normal atmospheric pressure, it doesn't melt into liquid COAOs. It goes straight from that solid ice to CuOEROs gas. The source points out practical uses for this ultra-cold process, like shipping temperature-sensitive things like vaccines, or even for special effects fog.
Interesting. And the reverse of that is deposition, gas straight back to solid.
That's right, like frost forming on a cold window pane.
Okay, now let's look at density. That's another key property linked to how particles are packed. The source defines it as mass per unit volume. Basically, how much stuff is crammed into a given amount of space.
Exactly, and the real insight here is what density explains. Why things float. It's simple, really. If an object is less dense than the fluid it's in, whether that's water or air, it floats. The source uses the classic example of ships. Huge, heavy things, but they float because their hull encloses a massive volume of air, making the ship's overall density much lower than water's density.
Right, it's the average density that matters. And the source mentioned another surprising example related to floating. Ice.
Yes, ice floating on water. Normally, you'd expect the solid form of something to be denser than the liquid form, right? But water is weird. The source notes that when water freezes, the azo molecules arrange themselves into a crystal structure that actually takes up more space than they do in liquid water. So ice is less dense. The source gives the numbers. About 0.92 grams per cubic centimeter for ice versus 1.00 for liquid water, and that's why it floats. A crucial property for life on Earth, actually.
Wow, okay. That's a really important exception. And less dense liquids also float on denser ones.
Absolutely, like oil on water. The source mentions they don't mix, they're immiscible, and the less dense oil floats on top.
And density changes with temperature.
It does, yeah. Generally, as temperature increases, matter expands slightly because the particles move more and push further apart. More volume for the same mass means density decreases.
The source had that density table. I remember seeing aluminium was much less dense, like 2.70 GcM compared to iron at nearly 8. Or lead over 11?
Exactly. And that density difference is precisely why aluminium is so valuable for making things lighter. Like modern car bodies, the source mentions. Lighter cars mean better fuel efficiency.
These basic properties have huge practical applications everywhere you look. They really do. And you mentioned expansion with temperature. That leads to thermal expansion and contraction.
Right. Materials expand when heated because the particles gain kinetic energy, they move more vigorously, and push each other further apart. That's what the particle model suggests. And they contract when cooled as particles lose energy, slow down, and move closer together. Solids, liquids, gases, they all do this to some extent.
And the source made an interesting point here. When something expands, it's the spaces between the particles that increase. The particles themselves don't get bigger, and you don't get more of them.
That's a key clarification, yes.
Okay, one last physical concept. Pressure. The source defined it as the amount of force applied over a given area.
Yeah. And fundamentally, this pressure, especially in gases and liquids, is caused by those constantly moving particles colliding with surfaces each other, the walls of the container.
Yep.
Billions of tiny impacts adding up. The key relationship the source notes, particularly for gases, is between pressure and volume. If you squeeze a gas into a smaller container, reduce the volume, the particles hit the walls more often and the pressure goes up. Increase the volume, give them more space, they hit the walls less often, pressure goes down. They're inversely related, assuming temperature stays the same.
That makes intuitive sense. More force on the same area also increases pressure, right? Like pushing with a sharp pin versus your whole finger.
Exactly. Same force, much smaller area, much higher pressure under the pin. All these behaviors, expansion, density, pressure, states of matter, they all link back beautifully to the motion and arrangement of those fundamental particles.
Okay, we've covered a lot on physical properties and changes. But substances can also transform much more fundamentally, right? Through chemical reactions.
Right. Now we're talking about forming entirely new substances, not just mixing things or changing their state. The source defines a chemical reaction as a process where atoms are actually rearranged. Existing chemical bonds are broken, and new chemical bonds are formed between different atoms.
So you start with your ingredients, the reactants, which are usually written on the left side of a chemical equation.
And you end up with products, the completely new substances that are formed, written on the right side.
The source gives the simple symbolic example. C plus O NS, carbon reacting with oxygen, yields carbon dioxide.
Yeah, a very common reaction. And it also provides a historical real-world example. Alcoholic fermentation. That's where yeast uses enzymes to react with sugar, like glucose, CeO, breaking it down to produce carbon dioxide, CO, and ethanol, CHOO, which is the alcohol. It clearly shows the starting substance, glucose, being chemically rearranged into totally different substances with totally different properties. Reactants yield products.
It's a tangible illustration of atoms just changing partners, basically, to create something entirely new.
That's a great way to put it.
So we've kind of completed our deep dive into these core concepts of matter and materials, using this Grade 8 guide as our source. We navigated from the atom itself through how elements are organized and how they combine into compounds with those fixed ratios.
How substances can also just form mixtures that you can separate physically, and how matter's behavior, its state, its changes are explained by the motion of its particles, influenced by temperature and pressure.
Yeah, and we pulled out some surprising facts along the way, like those liquid metals, mercury and gallium, or how dry ice skips the liquid phase entirely through sublimation.
We saw how density explains everyday things like why big ships float and why ice, strangely, floats on water, defying the usual solid behavior. And we saw how chemical reactions are really just the fundamental rearrangement of atoms into new combinations.
These foundational ideas, even presented in this straightforward way from the learner guide, are incredibly powerful lenses. They really help you view the entire physical world differently.
They absolutely are. They're the bedrock of so much scientific understanding.
Okay, so here's a final provocative thought for you, our listener, to consider based on everything we've discussed today. If the astonishing diversity and complexity of everything around us, from the vastness of space to the intricate biology of a living cell, or even just the technology you're using right now to listen, if all of that arises simply from different arrangements and behaviors of a limited number of fundamental particles obeying a few basic rules, what does that imply about the sheer elegance and the incredible potential hidden within simplicity itself?